Okay, test 3, flanking metal fence. Well, I accidentally, as it happens, repeated the experiment at a section of the road flanked by a chain link fence. Now, at that time, I used a signal with 9 carriers centered on 900 megahertz, separated by 15 megahertz, so I could see the effective frequency. And the spectrum looks like this, 9 carriers, 15 megahertz apart, and this is a playback of an example of the recorded spectra at the test site. My original objective was to measure RF power as the receiver antenna descended down an asphalt hill, which approached the flat part of the test range. But the hill part of the road is flanked by a chain link fence. Nothing I can do about it. It's 8.7 meters from the center line of the road. The fence is about 2.5 meters tall. It's capped with barbed wire and davits and canted towards the test range. It appeared to be well made, vertically true, and generally in good condition.
Now, whoever made the fence, they did a nearly perfect job. And if they hadn't done such a nearly perfect job, and if the fence wasn't so straight and true and in such good condition, it's unlikely to me that I would have discovered what I'm about to tell you.
So I made the measurements out to 180 meters. And here's what the whole measurement set looks like this. It's like, wow, that's a lot of noise, like spatial noise. And here's what the first 40 meters look like. There's also a lot of noise. And it doesn't look anything like the first 40 meters of the flat asphalt test range I showed you for the first test case. But otherwise, the experiment is the same, except for the side scattering metal fence. So follow my logic here. It relates to the propagation model. So here's the thinking. Now, the hill starts at about 40 meters from where I put the transmitter. So except for the effect of the fence, the measurements should perfectly match the first 40 meters of the earlier measurements, but they don't. So then I thought, well, maybe the primary reflection isn't from the road surface, maybe it's from the flanking fence. And the fence is made of metal, and it's only 8.7 meters away, and at 900 megahertz, a chain link fence behaves electrically like a flat metal wall because the holes in the fence are smaller than a quarter wavelength. Wavelength's 33 centimeters. That's about a foot. And a metal wall is one of the easiest things ever to represent electromagnetically and mathematically speaking. So, like an antenna pair beside an infinite metal wall. That's a textbook problem. It shouldn't even be real in the real world or exist in the real world, but it kind of does. So let's configure the data analysis software application to represent that case and then compare the predicted and measured powers. So forget the road, the transmitter and receive antenna need to be both 8.7 meters above the reflecting surface. And that's a change from 1.7 meters for the transmitter and 1.0 meters of the reflector, which that's their height above the road surface, so never mind the road. It's as though the whole orientation of the experiment has been rotated 90 degrees. And since I was using vertical polarization on the road, the polarization is parallel to the fence. So the polarization used in the model, the converted model, needs to be changed from vertical to horizontal. Also, the reflecting surface isn't asphalt anymore, it's metal. So let's use copper. I just don't have a steel model, but that doesn't matter. So now let's make those changes and see what happens. Remember, the yellow curve is the predicted power, and we want to see how closely the predicted power matches the measured power after the model is reconfigured to represent the metal fence, ignoring for now the forward road reflection, just for now. So first, let's disable the forward road reflection, so the predicted power is now just free space variation. Next, display the control panel for configuring the side scatter reflection and enable the side scatter reflector surface. Okay, we make the radiation pattern of the transmit and receive antennas isotropic, since the radiation pattern of a dipole looks like a donut and the fat part of the donut is pointing at the fence. So it's isotropic in the elevation plane. Next, change the polarization from vertical to horizontal, parallel to the fence. Change the reflecting surface from dry asphalt to copper. As I said, I don't have a dielectric constant and conductivity for steel, but that doesn't matter for now. Okay, change the antenna height from the transmit antenna height from 1.7 meters to 8.7 meters. And change the receive antenna height from 1 meter to 8.7 meters. They're both the same distance from the fence. So that's a little bit more interesting. Now change 8.7 meters to 8.6 meters for both receive and transmit antennas. Now that's much more interesting. Let's zoom in on the first 20 meters so we can see it in some detail. Okay, now let's take a closer look here, but first we'll change the dynamic range so we can see the graph a little bit better. Okay, we'll look at each carrier, and this is at 900 megahertz. Now it's interesting to see that the markers, the measurement markers, are lying almost perfectly on the predicted power level lines. You even see a null here and climbing up towards a peak, and these kind of dancing through, they appear to line up quite well with the measurements. That's at 900 megahertz. So let's go to 915. Same kind of story, really, here and here. They're not exact, but they're pretty close. Even there's a null predicted here, and we do see a low power measurement here. And so within the first 20 meters, there's that one doesn't quite line up, but pretty good. Here's 930 megahertz. Same sort of story. Look here, 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 here. We've got a bunch of measurements that seem to match fairly well to the predicted power levels. 945, again, here we see on the edge of a null, two of them creeping across, midpoint between peaks and nulls, another null here. 960 megahertz, the highest carrier, again, we have a null here, and these, that's not quite right, but, you know, it looks close. It's going down in frequency, 945, 930, 915, 900, 885, okay, not perfect, but there's something seems to be correct here about the predicted power levels. There's 870, another 15 megahertz down. This strange smooth structure here is just kind of dancing through the peaks and nulls, and the same structure here, which does seem to pretty much match up with the predicted power levels. Next, down one more step, 855. Yeah, okay, well, there's kind of a peak there. There's a null here, a null there. And the last one, 840. Well, it's probably the poorest of them all, maybe, but these two match. I mean, this could be confirmation bias, but I see a number of points that look like they are believably correct towards, you know, these are low power levels, but they are happening where we would expect to see some nulls. So overall, it seems that the measurements look quite good. So let's go back up to 900 megahertz. And what happens if we change the distance to the fence from 8.6 meters to 8.7 meters? Well, there's the transmitter up to 8.7, and here's the receiver up to 8.7. And then they don't seem to match quite as good anymore. And we can go to a, you know, up another frequency from 900 to 915. And I would say the match isn't quite as good. 930. Okay, but not as good as 8.6 meters. 945. Now we have a null predicted right where there's a peak. 960. Same story. And we can go down in frequency. 945, 930, 915, 900. Again, the point being that when we set the distance to the fence at 8.7 meters, which is what I measured it at, the agreement doesn't appear to be quite as good. So that tells us by these spectral measurements that the correct distance to the fence almost certainly was 9.6 meters. And we would be able to tell that by using a broad spectrum signal. We'd be able to tell that there's something nearby that's made of metal and it's 8.6 meters away. And by the way, if we change the reflecting material from metal to something else, the agreement is not as good. So let's just see what that looks like. Take these back to 8.6, transmitter to 8.6, and the receive antenna to 8.6 meters. Now, when we change to, for example, dry asphalt, the agreement is poor, or dry earth, or wet sand, or dry sand, sea ice, sea water. The agreement is not as good as if we use metal, it seems. So Yeah, we can tell that the object nearby is most likely made of metal, certainly because of the depth of the nulls that we see at some frequencies. So the overall conclusion is that the propagation model appears to produce fairly good agreement with the measurements in this test case, even though the measurements look like noise. The trick is that the model must be configured to represent the actual conditions of the experiment. Then we're good to go.